In this class, we look at some more aspects of formulating linear programming problems. We now look at the formulation of manpower requirement problem. The problem is as follows. The daily requirement of nurses in a private nursing home is given in the following table. Now, this is given as 6 time slots in a day, each time slot being for 4 hours. For example, 8 a.m. to 12 noon we require 12 people, 12 noon to 4 p.m. we require 15 people, and so on. The nurses who come to work can start work at the beginning of any of these 6 slots, which means they can start working at 8 a.m. or 12 noon or 4 p.m. or 8 p.m., 12 midnight and 4 a.m. They can start working on any of these hours, and they work for 8 continuous hours. What is the minimum number of people required to meet the daily demand? We also make an assumption that a person who starts working at 8 a.m. works in the slot 8 a.m. to 12 noon as well as in the slot 12 noon to 4 p.m. Again, a person who starts working at 8 p.m. would work in the 8 p.m. to 12 midnight slot as well as in the 12 midnight to 4 a.m. slot. So, that is how the 8 consecutive hours are coming. So, the problem is how many people start working at the beginning of these 6 time slots such that we have minimum total number of people working and we are able to meet the requirement or demand of each of these time slots. Since there are 6 time slots, we have 6 variables, and we define these variables as x1 to x6. So, x1 to x6, let it be the number of nurses who start work at the beginning of these 6 slots, which is 8 a.m., 12 noon and so on. Now, the objective function will be to minimize the total number of people who are working, and therefore, it is to minimize x1 plus x2 plus x3 plus x4 plus x5 plus x6. Now, that is shown here as the objective function here, x1 to x6. It is also shown in the form of a summation where this sigma j equal to 1 to 6 xj when expanded will give x1 plus x2 plus x3 plus x4 plus x5 plus x6. So, the objective function will minimize the number of people who are working who come to work in the beginning of these 6 slots. Now, the constraints are to meet the requirement of the 6 slots. For example, x1 plus x2 is greater than or equal to 15. Now, x1 plus x2, the number of people who actually work in the slot 12 noon to 4 p.m. If we see 12 noon to 4 p.m., 15 people are required, but we also observe that people who start working at 8 a.m. work for 8 hours, and their 8 hours includes 12 noon to 4 p.m. People who start working at 12 noon also work for 8 consecutive hours, where 4 hours between 12 noon and 4 p.m. and another 4 hours between 4 p.m. and 8 p.m. Therefore, the number of people who are working in this slot, which is between 12 noon and 4 p.m. are those who start working at 8 a.m. and those who start working at 12 noon. So, x1 plus x2 are the number of people who actually work between 12 noon and 4 p.m. and therefore, x1 plus x2 should be greater than or equal to 15, and we should be able to meet the requirement of period 2, which is given by 15 as the requirement. So, similarly, x2 plus x3, the number of people who actually work between 4 p.m. to 8 p.m., that should be greater than or equal to 10. x3 plus x4 should be greater than or equal to 8, x4 plus x5 is greater than or equal to 6, x5 plus x6 is greater than or equal to 10, and x1 plus x6 is greater than or equal to 12, because to meet the 8 am to 12 noon, those who come to work from 4 am to 8 am will be working in this slot. People who come to work at 8 am also work in this slot. So, this 12 requirement is to be met with x1 people who start work at 8 am and x6 people who start work at 4 am. So, we have these 6 constraints which represent the requirement of the 6 periods to be met. What is important is to understand that both x1 and x2 are the number of people who are working in the second period, x2 and x3 work in the third period, and like that x6 and x1 work in the first period. Now, all these variables x1, x2, x3, x4, x5 and x6 have to be greater than or equal to 0. Of course, one may ask that these x1 to x6 representing the number of nurses should also take only integer values. So, is it necessary to introduce these variables also as integer variables? Now, at the moment we choose not to represent them as integer variables. We are interested in formulating linear programming problems. Therefore, we expect and define the variables to take continuous values. If we put explicit integer restriction on the variables, then the formulation becomes linear integer programming. But at the moment, since we are doing only linear programming, we are defining these variables to be continuous variables. So, this simple formulation have taught us a few things. In this formulation, the objective function is a minimization function, unlike the maximization function in the last example that was done in the last class. Here the 6 constraints are greater than or equal to inequalities, unlike less than or equal to inequalities which we saw in the previous example. So, based on the 2 examples, we will be able to say that the objective function is either a maximization function or a minimization function. The constraints are either less than or equal to type inequalities or greater than or equal to type inequalities. They can also be equations. There is a non-negativity restriction on the variables. Now, we look at a third formulation where we look at production planning situation. We consider a single product and a company making this product. The demand for 2 weeks for this product are 800 and 1000 respectively. In a week, this company can produce up to 700 units using their regular time production, and it costs rupees 100 per product made or per unit made. The company can also employ overtime and produce up to an extra 300 units in a week. Now, the cost of making that unit through overtime is 120 per product. The company can also produce a little more in the first month if it is possible and use the excess from one week to another, and the cost of carrying this excess inventory from one week to another is rupees 15 per product per week. How should they produce to meet the demand of the 2 weeks at minimum cost? Now, we introduce 5 variables. X1 be the number of products made using regular time in week 1, x2 be the number of products made using regular time in week 2. Week is the unit of time that we are looking at in this example. Y1 is the number of products made using overtime in week 1, and Y2 be the number of products made using overtime in week 2. Now, Z1 is introduced as the number of products carried from week 1 to week 2 after meeting week 1's demand. So, there are 5 variables in this formulation. The objective function is to minimize the total cost. 100 x1 is the cost of producing x1 units in week 1 using regular time. 100 x2 is the cost of producing x2 in week 2 using regular time. Y1 is the quantity produced in week 1 using overtime and therefore costs 120 Y1. Similarly, 120 Y2 is the cost of producing in week 2 using overtime, and 15 Z1 is the cost of carrying the Z1 items from week 1 to week 2. There are 5 terms, 3 distinct costs: regular time cost for 2 weeks, overtime cost for 2 weeks, and cost of carrying the excess inventory from week 1 to week 2. Now, we look at the constraints. The first constraint is to satisfy the demand of the first week. So, this is written as x1 plus y1 equals 800 plus z1. 800 is the demand for the week which is to be satisfied. If we produce more than 800, the quantity z1 is carried to the next week. So, whatever is produced in the first week should meet the demand of the week and the excess that is carried to the second week. Therefore, x1 plus y1 is equal to 800 plus z1. Now, this is rewritten as x1 plus y1 minus z1 equals 800. It is customary to write the constant in the right hand side of the equation or the inequality, and the left hand side of the equation or inequality contains the variable terms. Now, this particular constraint is an equation. So, the actual constraint written in a standard form is shown in a different color here. Now, the constraint for the demand of the second month or second week is x2 plus y2 represent the quantity produced using regular time and overtime in week 2. Z1 is the quantity carried from week 1 to week 2. Therefore, what is available to meet the demand of week 2 are the 2 production quantities x2 plus y2 and the excess inventory that is carried, which is Z1. So, Z1 plus x2 plus y2 equal to 1000 is the constraint to meet the demand of the second week. We also have capacity restrictions where x1 is restricted to 700, so less than or equal to 700. x2 is less than or equal to 700, represents the capacity, regular time capacity in the 2 weeks. y1 less than or equal to 300, y2 less than or equal to 300 represents the overtime capacity in the 2 weeks. So, there are 6 constraints, 2 constraints to meet the demand of the 2 weeks, which are expressed as equations. The remaining 4 constraints are inequalities, less than or equal to inequalities, because they represent the limit on regular time production and overtime production in the 2 weeks. There is an explicit non-negativity restriction given by x1, x2, y1, y2 and z1 greater than or equal to 0. So, this completes the formulation of this problem. Now, let us look at the same formulation in a slightly different way. Now, the objective function is once again written in a slightly different way. It is now written as 100 x1 plus 100 x2 plus 120 y1 plus 120 y2 plus 15 into x1 plus y1 minus 800. Now, z1 has been left out and z1 has been replaced as x1 plus y1 minus 800 from this equation. So, I am leaving out or eliminating the variable z1 and writing it as 15 into x1 plus y1 minus 800. Now, this is obtained from this equation. So, this is rewritten on simplification as 115 x1 plus 100 x2 plus 135 y1 plus 120 y2 minus 12,000. The rest of the constraints are x1 plus y1 is greater than or equal to 800. What is produced in the first week is either equal to 800 or more, and if it is more, the excess is carried to the second week. So, what is carried to the second week is x1 plus y1 minus 800. So, this z1 is now written as x1 plus y1 minus 800, and on simplification we will give x1 plus x2 plus y1 plus y2 is greater than or equal to 1800. Because the z1 is x1 plus y1 minus 800, the minus 800 goes to the other side of the equation to give us x1 plus x2 plus y1 plus y2 is greater than or equal to 1800. The 4 capacity constraints remain the same. Now, there are only 4 variables because the variable z1 has been left out. So, all the 4 variables are greater than or equal to 0. Now, if we compare these two formulations, we may also wish to say that x1 plus x2 plus y1 plus y2 could be equal to 1800 or it could be greater than or equal to 1800. For example, if we substitute z1 as x1 plus y1 minus 800 into the second equation, here the second equation would become an equation instead of an inequality. However, since the first constraint is written as an inequality, we simply maintain the consistency and write this as greater than or equal to 1800, because x1 plus x2 plus y1 plus y2 would represent the total production in the 2 weeks. This represents the total demand in the 2 weeks, and because there is no third week in this particular example, we will not end up making more than 1800 if we look at the production of the 2 weeks taken together. So, it is alright if we write a greater than or equal to inequality here instead of an equation. So, the new formulation now has eliminated one variable and has 4 variables which represent the 2 variables which are regular time production quantities in the 2 weeks and another 2 variables which are overtime production quantities in the 2 weeks. Now, there is also a constant term in the objective function, and when we actually solve this, we can leave out the constant both from the formulation and to begin with in the solution, and can add that. So, this will be rewritten as minimize 115 x1 plus 100 x2 plus 135 y1 plus 120 y2, and we can leave out the minus 12,000 and add it as and when required. There are again 6 constraints, 2 for the demand constraints and 4 for the capacity constraints. Now, in this formulation, the two demand constraints are greater than or equal to constraints, and the 4 capacity constraints are less than or equal to constraint. So, in the second formulation, we have one variable less and the constraints are all inequalities instead of equations. In the next class, we will see some more examples in formulating linear programming problems.